Hi everybody, a very warm welcome to this new VTM webinar called the Boundaries Optimization. The Codecs War is not over. My name is David Jarbolet. I'm in charge of business development for the APAC region, and I'm currently based in Singapore. I will be acting as a moderator today for this session. I can see that we have a pretty large audience, which is very good, from people coming from all over the world. So once again, very warm welcome. To discuss this different topic today, I have three speakers with me that I will briefly introduce. The first one is Yan Ye. So Yan is currently the head of the video technology, XJ Lab, Damo Academy of Alibaba. She has an extensive experience in video codec development and implementation, and she has been involved in development of various codecs like VTM, HEVC, H.264, MPEG- or MPEG-OMAP. She's also an inventor of more than 100 granted US patents, and she has published in more than 50 papers in peer-reviewed journals and conferences. She has received her PhD in electrical engineering from the University of California in San Diego in 2002, and she's currently based in Sunny Valley in California. Today she will talk about VVC, and she will present the VVC history, the versatility feature, as well as the latest performances. Yan, thank you very much for joining us, especially taking into account the time on your side of the world. That's much appreciated. Our second presenter today will be Michael. Michael is our VP Innovation at ATM. He's based in Rennes, in the west side of France, and is currently leading standardization efforts at ATM, working on different activities and multiple subjects like HEVC, DDB, -IF, UHD Forum, and is working as well on multiple projects with the R&D team. He has received his PhD in 2006 from the National Institute of Science of Rennes, INSA. And today we'll tell us about what's next in the Codecs War, comparing multiple codecs like HEVC, VVC, AV1, or EVC. Thanks, Michael, for that. And last but not least, Jean-Baptiste. Jean-Baptiste Kempf is the president of Videoland. Videoland being a non-profit organization created in 2008. He's also one of the lead developers of the open source media player, VLC. He's working with various video-related startups, and he has founded Video Labs, which focus on open source multimedia technology. He has a deep knowledge in different aspects of computer science, like open source development, high-performance computing programming, or information systems specification. He has a master in computer science research at the École Centrale of Paris. And today he will tell us more about Videoland, the open source community. Thank you, Jean-Baptiste, as well, for joining us. A quick view on the agenda. So we'll start with Yan Ye, with the VVC deep dive, followed by Michael on what's next in the Codecs War, and then Jean-Baptiste will conclude with the Videoland, the open source community. We will have as well Q&A section at the end. So before we jump into the presentation, we have a couple of guidelines. So everybody's on mute, but you can still ask questions via the Q&A button. So don't hesitate to write any question that you may have during the presentation. We'll try to respond one or two at the end of each presentation, and at the end of the webinar, we'll try to respond as many as possible. So last, before we start, I'm launching a quick poll right now of the question of the day. The question being, what could be your main reason to move to another codec? Will it be the boundaries improvement to increase the number of services, the end-to-end ecosystem maturity, hardware widely deployed, the higher resolution and higher frame rate, or could it be the codec fee for the licensing? So you can reply, just select the response that you want. I'll give 30 seconds to a minute, and then I'll end the poll and maybe show the responses before starting with the presentation of yeah. Ten to 15 more seconds. Excellent. So let's close this. And polling. So if I share the results with you, that's interesting to see that for more than half of the respondents, boundaries improvement to increase the number of services is the key element, or actually the main reason to move to another code. Excellent. So I will stop sharing my screen, and Jan, you can take over from there.
Okay, thank you, David. Let me share my screen. Can you see my screen?
Yes.
Okay, good. So let me, if I could only put it on. What happened to my, sorry. Oh, it really is getting late, I guess. Okay, there we go. Sorry about that. So thank you for the opportunity to talk about VVC. I will present VVC deep dive, as deep as we can get in 20 minutes. Let's see how that goes. So a very brief outline. First, we'll look at a history of the MPEG and ITUT video standards. We'll look at VVC project by itself, its goals, timeline, and so on. Look at some coding tools as much as we can. And then certainly we want to take a look at the versatility features of VVC. And last part is on VVC performance. So on this slide, you see kind of a family tree of the different generations of ITU and ISO IEC MPEG standards for video codec standards, that is. We started basically in early 1990, and this is right now roughly the 6th generation. VVC is the 6th generation. And some of these codecs are developed jointly by the two organizations. And they are very widely deployed in the market and enjoy very nice commercial success. So why do we do this, right? Why do we keep generating different generations of codecs? Certainly, coding efficiency is the foremost reason for that. So for every 2 generations, we always try to achieve a bit rate reduction of 50%. And that is the same for VVC. That's what we are targeting, a reduction of 50% at the same subjective quality to move the coding efficiency curve further to the left. So before I start diving in, a few acronyms. VVC stands for Versatile Video Coding. It is developed in the joint team called JVET. It's a joint team of the 2 organizations. And before VVC, we had a joint exploration model, or JEM in short, to help us do the coding tool technology development. And after VVC started, we've been using VTM, which stands for VVC test model, and the latest version is VTM 9. So before it all started, VVC really didn't come out of thin air. There was a lot of hard work, almost 3 years of pre-standardization technology development. The work started in early 2015, actually, in VCAG as the 4th generation KTA study. And then later that year, we moved into a joint team to develop coding technology together. And for about 2 years, there was an evolution of the JEM, the test model, the exploration model that we were using at the time, 7 different versions for SDR video. And by the time we are at the 7th version, we achieved 34% bit rate savings compared to HM. And that is when we said, let's also start a call for evidence to see that the technologies are ready for standardization. And in 2017, July, we had responses that showed that we're ready to do standardization. So here came the CFP. It was issued jointly by the 2 organizations, ISO IEC MPEG and ITUT VCAG, in October 2017. I would like to note that it is the first CFP that included 3 categories of video content. Besides SDR, which is the mainstream video format, we also included HDR and 360-degree video. In about half a year since the CFP was issued, in 2018, April, 23 CFP responses were received and evaluated. These came from 32 organizations worldwide, so the participation was very highly participated, I would say. And back then, even at the CFP stage, the top submissions already showed that we could achieve 40% or more bill rate savings in terms of PSNR over HEVC. So basically, you know, as we saw in the CFP, we consider different types of video content. So VVC design goal was certainly including the coding efficiency aspects. You know, we wanted that 50% bill rate reduction. But we also consider versatility from the very beginning. And what I mean by versatility is that VVC wants to look at more formats, more types of video content, the SDR in different resolutions up to 8K, also HDR in 10 bits, 360-degree video for VR applications, and also screen content for what we're doing now, things like screen sharing. We also, along the way, included more features, and I'll talk about these later in the slides to address the needs of more applications. So in terms of its timeline, we started in October 2017 with the joint call for proposals. And then in 2018, April, we started with VVC test model version 1. We went through 9 iterations since the April meeting was the VTM 9. And we're almost there. So next month, we will hit the milestone of the VVC version 1 final draft international standard. Almost there. So on this slide, I show you an evolution of the VTM, the capability. So what the blue bars are the coding efficiency that different versions of VTM achieve, from VTM 1.0 all the way up to VTM 9.0. And the orange line is the encoding complexity as in terms of encoding time. And the gray line is the decoding complexity in terms of decoding time. So I want to just draw your attention to the fact that, you know, basically you can kind of see 2 phases of VVC development. The first phase is roughly between 1.0 to 5.0, where you have a rapid increase of coding efficiency. And with that, of course, comes along the rapid increase in encoding complexity as well, because you were looking at including more coding tools, and therefore the encoder needs to work harder to achieve the coding efficiency that it can achieve, do the best mode selection. And the second phase basically starts, I would say, from VTM 6.0 on. The design starts to stabilize. We still have been adding some coding tools, but at a slower pace. And the coding efficiency will gain maybe 1%, 2% between meetings. Coding time and complexity kind of holds steady because of that. And by VTM 9, basically we achieve a 39% rate reduction. Thank God it's not 3.9. 39% rate reduction in terms of PSNR, which is roughly the same ballpark gain when you look at HEVC when it was being finalized compared to AVC. So how did we achieve that? You know, there's actually quite a few coding tools that VVC supports. So I apologize for kind of the busy slides. I color-coded different categories of coding tools just to show you that really, you know, we consider every aspect of a hybrid video coding system, from block partitioning all the way to residual coding, transform, entropy, loop filter, all of the blocks, building blocks. I highlighted a few by the boldface, so kind of just quickly touch upon those. For block partitioning, we support up to 128 by 128 CPU size. The block partition, in addition to quad tree, which is available in HEVC, we also support binary tree and ternary tree, which we collectively call multi-type tree or MTT. For intra-prediction, we have a tool that is a cross-component linear model tool that allows you to predict chroma signal from luma signal. And for inter-prediction, we have a rich set. Just quickly talk about a few of them. Affine motion, in addition to conventional translational motion, VVC supports 4-parameter affine or 6-parameter affine. And it also allows you to do at the block level, adaptive motion vector resolution. So you can choose between quarter-pale motion, 1-pale motion, or 4-pale motion. And we also have a tool called geometric partition mode, which allows you to partition a block into not just horizontally vertically, but in a slanted angle. In terms of residual coding, VVC supports dependent quantization, which is a flavor of trellis quantization, achieves very nice gains. Transform, besides the conventional DCT2, we have other core transforms based on DCT and DST, also a secondary transform, and transform size can be up to 64 by 64. For entropy coding, we swapped out the entropy core engine with a new one that is more powerful. And loop filter, we have a few new ones, adaptive loop filter certainly, and also a tool called Luma mapping with chroma scaling, achieving good gains. Of course, we also have coding tools for screen content and 360-degree video. We'll talk about those later. So here, this figure shows, we saw like 30-something tools, I think 33, 34 tools. Each of them is represented by a color-coded dot on this figure. So the figure, the horizontal axis is represents coding complexity. So the figure shows actually the more to the right, the lower the complexity. That's just the way to read it. And the vertical axis is the coding efficiency. So you want to have a tool that's kind of on the top right-hand side of the figure. I know that we have a lot of tools, but tools that have above 1% coding gain by itself, there is only 6 on this figure. There are 2 more, which is the Codec engine and the MTT, the multi-type tree that I just mentioned. They also achieve more than 1% gain. Actually, MTT achieves almost 10% gain. But a lot of these tools are smaller incremental gains rather than bigger gains. So let's now, move into the versatility area. The first one, just talk about some different types of content, how does VVC handle them. So the first one is screen content. We do screen sharing these days more than ever. Also, cloud gaming is another application, emerging application. These screen content, if you use tools that are designed for natural content, they don't always work very well. So VVC, the version 1 supports some screen content tools like intra-block copy, transform skip with a new residual coding methods, block DPCM, and there's also palette and adaptive color transform, although they're not in the main profile. So what VVC tries to do for screen content is to have a main profile that provides better support for screen content coding than the HEVC main profile. So the second type of content is HDR. Starting from the very beginning of the call, we consider HDR 2 types of mainstream transfer functions, PQ and HLG. We did eventually decide not to include any HDR-specific normative coding tools in VVC, we have a non-normative method implemented in the reference software that is adjusting the QP based on luminance level of a block. And we also have a HDR tool software package that you can use to play with the HDR signal. Moving on to 360 video for VR applications. We have one 360 specific coding tool in VVC. That is the horizontal wraparound motion compensation. This tool mainly improves subjective quality at the picture boundaries of a ERP or ERP-like projection format. We also have a look at non-normative methods such as we can adjust the QP at the block level based on the spherical sampling density of your projection format. Same as HDR, the JVET has a 360 lib reference platform that you can use to do projection format conversion, coding, and quality evaluation of this type of video content. So now let's look at some other features, not just different types of video content, features supported in VVC for versatility. In HEVC and also in AEC, all the pictures in a sequence must have the same spatial resolution. And if you, for example, your bandwidth goes down, you need to, you can't send HD, you have to send 540p, you have to start with a new sequence that comes with a new intro picture, and that causes rate spike, which is not desirable. So we have a tool called reference picture resampling, or RPR, that enables interprediction between pictures that have different spatial resolution. So in VVC, you can do up to 2x downsampling and up to 8x upsampling between the current picture and its reference. So with that, what you can do, in the figure below is if your bandwidth goes down, you can downscale, for example, by 1.5 times. And then your bandwidth still is bad, it gets worse, you downscale again by another 1.5. And when it improves, gets back, you can scale it back up to the original resolution. And this way, you can continue doing this without breaking the temporal prediction, and therefore you don't cause a rate spike to accommodate applications like video conferencing, like what we're doing now. So with RPR, basically layered scalability with spatial scalability is basically a given, because what that requires is really just interlayer prediction from a reference picture that has a different resolution, which RPR already addresses. So because of that, VVC version 1 supports layered scalability of different spatial resolutions. And other features include parallel processing. Pictures are getting bigger. So VVC supports tiles, slices, wavefronts, WPP for parallel processing. And for slices, in addition to the raster scan slices, VVC also supports the rectangular slice mode that is shown on the picture on the bottom right side. That is a more rectangular shape. VVC also supports subpictures and virtual boundaries for coding of 360 video. So now let's take a look at the performance. For this one is the SDR, CTC, common test condition that we use. It shows all info for still image coding, random access for entertainment applications, low delay for video conferencing. Table summarizes different classes of sequences and the average gain we can achieve. For random access, the mainstream application we can achieve for HD and UHD combined, we can achieve 37.6% coding gain. And I wanted to say that this is based on VTM 8. VTM 9 has another percent, a little more than 1% gain on top of VTM 8. And complexity is, decoder is quite reasonable. You have 2x compared to HM. And the encoder is, of course, has to work a lot harder. So, video is not just about, PSNR. It's also actually more about subjective quality. So we have started doing verification testing for VVC using formal subjective testing protocols. Because of the pandemic, it's difficult at the moment to get naive subjects to conduct the tests. So we have gathered some expert viewers to look at the video between between HEVC and VVC. And these two sequences, the top ones are the average MOS score between the two codecs. And the bottom one shows the bit rate that is used to achieve the MOS score. So what you can see for these two sequences are that toward the kind of on the right-hand side of the figure, toward the higher bit range, higher quality, VVC achieves similar quality, and toward the lower end, VVC quality is significantly higher compared to HEVC. But let's remember that such quality, whether they're the same or higher, actually is achieved at a much lower rate, as indicated by the curves below. So HDR, this slide summarizes HDR. Due to time, I won't go into details. It's basically similar observation as SDR, significant coding efficiency gain. And 360 video, also, if you look at the codec comparison, that's the middle table here, we can achieve about 29% coding gain, and you can use more advanced projection formats to push that gain up to almost 33%. That's shown by the bottom table here. So in summary, VVC offers the best compression performance compared to the other codecs on the market. It achieves 39% PSNR based on bit rate reduction. And we do think subjective testing will show even more gain. And VVC is designed with versatility in mind from the very beginning. So we consider different types of content. We also have more features, including more features to accommodate the needs of different video applications. And finally, we're almost there. And I personally am really looking forward to seeing some early market adoption of the codec. And this slide is just a list of documents that I used to compile some of the data that I showed on the slides. And thank you very much for your attention.
Thank you very much, Nian. Wow, that was interesting. Thanks a lot. And you have been perfectly on time. Excellent. Well done.
I try.
Well done. So while we will hand over to Michael for the next one, maybe just a quick question from the attendants about the live parameter. So live transmission, sorry. You have seen all of those parameters, right? The question is, how can those parameters be optimized during a live transmission?
So by live, I assume that we're talking about real-time encoding. Is that right?
I assume so as well.
Yes. Okay. Sure. Yeah. No, that is a very excellent question, right? I think certainly in the live transmission, you have to cut corners, right? You can't do exhaustive search or even close to exhaustive search to find the best mode. So there are many encoding algorithms, speed up algorithms that you can do. For example, one bottleneck, if you have a lot of different kinds of partition modes that the standard supports, that tends to chew up a lot of your encoding time. So there is different types of technology now on the table. You can use some heuristics to guide you to do a content analysis for smooth area. Just pick the bigger partitions and don't further split. You can try to see whether your texture is going horizontally or vertically and decide your partition accordingly. And now with AI technology, a lot of people are experimenting with picking partition modes using some, machine learning methods. So all sorts of speed up for partition modes. And certainly for other things like, intro prediction, for example, which direction do you go with? You would be able to do some content analysis to predetermine that instead of doing an exhaustive search. So yeah, I mean, there's a lot of work that needs to be done to enable this for live. Yeah, but I think, you know, it's the same thing for HEVC. AVC probably is mature, but you know, even HEVC nowadays, if you want to achieve very high quality HEVC real-time encoder, a lot of people go to hardware solutions rather than software solutions.
Okay, cool, excellent. Thanks for that. So I'll keep a couple of other questions for the end of the webinar. And I guess, Michael, you can take over and share your screen for the next presentation.
Can you hear me?
Yes.
Yes.
Good. So I will speak about the next-gen codec. What kind of codec do we have today, and comparison between HEVC and the others, and also what's happening in 2020. So VVC is one of them, but there is another one that is also upcoming from MPEG, and I will speak about also this one. So the question is still the same. So do we need better video compression? So that's market analysis that was done by Cisco. So the video traffic is still increasing. We still want a better video quality. And when I was for HEVC, everybody was thinking that HEVC was the last encoder. Or at least we cannot outperform this one. And if we look at the presentation of Jan, we have at least 2 generations now of codecs that are outperforming HEVC, but by twice. So meaning by 4, which is quite impressive for all of us, and that is bringing that to the audience. And also that we are having UHD, 8K is upcoming. We have to handle HDR and white color gamut. Probably with 8K, it will be also come with higher frame rate. People are looking at 360 as well, and so SCC is for screen content coding. That's also something that people are looking at when we are, like today, sharing our screen. So the people are willing to have the best video quality at the end. So that's a way of where screen content coding can be used for encoding PowerPoint, for instance. So well, yes, we still need some more video compression. If we are looking at 8K today, the current implementation that has been done real time is at 100 megabits per second, so it's quite high. And nobody can, or at least not so many people can look at this particular content live. How do we handle this at ATEM? So we are still a small company. We are growing, but still a small company. So we don't have the same effort than the others in the standardization activities. But we are following MPEG and ITU, so that's where the birth of most of the codec are coming from. And then you have standardization bodies like SIMT, DVB, ATSC, or 3GPP that are using what MPEG is providing. And lately you got, so I put that in the forum, they are not doing standard as per the Alliance for Open Media that is doing some specification, and at the same time also an implementation of a codec. So the Alliance is working since 2015 or 16 on also providing some codecs, mostly for the internet community. And there is another forum that is looking also at what VVC, so the burden or the issue that we got for HEVC, they don't want to replicate that. And there is another forum that is looking at what could be the business model for VVC, the licensing that can be done for VVC, and that's the Media Coding Industry Forum, so the MCIF. And on our side, we are contributing to VVC based on a research project. So we have the ability in France and in Europe to collaborate with partners. So JB is also part of this project. So we are working together to do a first implementation of VVC, and I will showcase the first demonstration at the end of the presentation. We have other projects that we are working on, but that's the main project as of today. So it's a French collaborative project led by Thales, where we are working on that together. So I will do a short introduction on the goals, and then I will also explain some VVC technical details, not at the same level than Jan, but just to explain the difference in between codec. And then I will speak about so HEVC, that is the one that is upcoming this year, and that will have true deployment because we have the hardware that is available for the decoders. And also HEVC, that is the next gen codec that is also arriving at exactly the same date than VVC. So Jan was having a simpler codec history than I have here. But if I look at our market, so the codec that are used as of today are the green one, so the one that also Jan was mentioning before. And so the other green that we are having here is HEV1 and HEV2. So that's the other upcoming codecs that are arriving. And then starting from HEVC at MPEG, there is two other codecs that are also arriving this year or later this year. So VVC in July, HEVC in July, and LCVC later this year. So that's the three codecs that are arriving at MPEG. And HEV2, I will give a rough estimate, but it's a bit hard at the moment to predict for HEV2. So same than Jan, I'm just adding here some order of complexity. So when you move from one codec to another codec, it's not for free, and you also see that on the slide from Jan when everything is starting from the first version of the VTM to the latest version. You see an increase. In the end, you have an increase in between codec of about 6 to 10x in comparison between each of the codec. The goal, I'm not putting some of the codec that have not succeeded yet, but in general, a success of a codec is becoming when you are having 50% gain. And the initial question from David, there might be a shift as well, also on the licensing. So that's why you are having HEV1 really close to HEVC in terms of BD rate and yes, let's say that the curves are really close, but in the end there is another alternative that is upcoming as of today is the fee. So maybe one can adopt a codec based also on the licensing. So that's the landscape for the HEVC licensing. So MPEG LA is not coming from MPEG, just not to say something wrong from the community. So ISO doesn't have any rule for doing the licensing. So either the codec is coming for free, or it lets to others to decide how much it will cost, and how much it will cost will come after the codec is finalized. So we got several pools for HEVC, but you have to be aware that HEVC was having only a single pool, but many companies were still managing their own patents individually. So even if there was a single pool, there was still some companies that were managing the patent fees. And for HEVC, the only issue is that we are having is that we have more patent pools, but also some companies that are taking that outside of the pool. And the licensing was quite a burden for HEVC because they didn't manage to be able to have that really early after the HEVC was adopted by the industry. And if you see, all the mobiles have HEVC as of today, and all the TVs was having HEVC really early after the completion of the standard. Something that also delayed in the HEVC adoption is HDR at some point. So what's the situation at MPEG? So MPEG has been developing a lot of standards based on video, and they believe this has to be where the birth of all the codecs should be in the future, and from the past as well. But there was a threat from AOM with AV1. So Leonardo Chiariglione, that is the convener of MPEG since almost the very beginning of MPEG, was launching all the other alternatives. So we got VVC starting, and after VVC was starting, we got EVC. And there is also something that the industry was taking care about, is what I was saying before, is that you have now the Media Academic Industry Forum that is looking at how much the standard can cost. And the same way, if there is a tool that is costing too much, you have the ability to switch it off. So that's also a way of removing some burden on the cost of a codec. So we have VVC. VVC was started in October 2017. We have EVC that was started a year after. So you can see that as a fork of VVC, with some company that was providing EVC as the basis for the standardization activity. But they got really nice results from the very beginning, not like what VVC was doing. So it's a fast track at MPEG, around 18 months, a bit more, but the idea is to fast track the activity. And at the same time, you have AV1. AV1 was supposed to start in 2016 with the first code base released. And then we got the release of the AV1 specification in October 2018. And we were able to have some hardware demo just a year after the standardization or the specification was finished. So which is quite good. So if we predict that for the VVC and EVC, putting 2022 is a good number for having hardware for both. But the issue you may have is that you have two codecs at the same time. So maybe it will delay a bit the adoption from the industry at the receiver side. And if you look at AV2, so they should have decided what the code base is. So I'm not saying that at the moment it's not yet done. So it should be in January 2020, and we are a bit far than that. But the code base is not yet selected. We know which, at least it's reduced code base, I would say at the moment. And we can foresee, because they have two issues at if we can say that issue, is that they still have to perform 50% improvement, but with at the end a royalty-free codec. So the challenge is even more harder than what MPEG is doing on their side. So we can foresee it in between 2023 or 2026. So Jan was mentioning that, but there is no evolution at MPEG on the codec side. So the hybrid codec structure is still the same since almost MPEG 2. From MPEG 2 to H.264, you have one difference, is that you have in-loop filters, but the rest is exactly the same when you look at it at a higher level. The only thing that you are having is that each of the blocks are becoming more and more complex, and you are having more and more tools in each of the blocks. So we are currently at VTM 9, and we are at 40% improvement over HEVC right now. So one of the biggest differences, if you look at a picture, is AVC was working on 16 by 16 block, HEVC was working on 64 by 64, and VVC is looking at 128 by 128. So it has some impact on the hardware. So that's also something that you have to take into consideration. Why we haven't done that from the very beginning. So that's because the hardware was not able to handle that. Now we can, and also the resolution of the picture is becoming higher and higher. And you have some small blocks around the Eiffel Tower. So that's where you are having some details on the contours. So it was only square blocks before, and now we are having rectangular blocks in the latest specification. Something that also happened for the motion compensation is that you have also some triangles or trapezoidal forms. So that's something that is really new in a codec, or that can also be part of the AOM specification. So that's a slide that Jan was mentioning before. Just small word on this one. So the decoder complexity is quite important at MPEG. So we don't want to go higher than 2. And you are seeing that you have even a decrease, and that's true that VTM 5 is in the middle of the standardization process, 18 months. So when we start the community draft, what we are seeing at MPEG. And then we are reducing the complexity in general of the codec, and still keeping the BD rate improvement. So it's quite important for us because we are an encoder, live encoder company, so we are looking at the complexity as well and what we can do in the end. So just to come back on the other codec, so everyone is a royalty-free codec. So we have worked with VLC to provide a specification for MPEG-2TS, but it's mainly an OTT codec. So it has been designed by the internet community. Let's say people that was looking at the web browser and that was willing to still see video on their web browser. So Mozilla with their Firefox and other people that the burden of the cost of the fees on them was taking too much part. You can see that we have a lot of companies in the area of internet. We have also some content providers like Netflix. So many people are participating to this, and all the GAFA are part of it. So you can see that also Apple is part of the alliance. So what can we say? So the goal for them was having 20% of the state of the art, and since they are comparing to their existing codec was VP9, and their current structure of compression. So it's a bit difficult to compare the two when you want to compare AOM codec with MPEG codec. Something that is quite interesting that was also available in earlier codec is the film grain synthesis. So you have also the scalability, something that is rather similar to what VVC is doing today, and also the ability to encode screen content coding. So just a slide on this one. So everyone has also the scalability the ability to do 128 by 128. So we have also more intra prediction than what we have with HEVC. We have more transform size. So that's something that is also coming with everyone. And you're also seeing something that is rather similar than HEVC with some. So it's only square blocks for the intra prediction, and then you can have some rectangular blocks for the motion estimation. Something that we are working on, and that I think it's something that we are pushing a bit more, is we are facing some issue with HEVC and all the codec, is that it's removing in general the grain, and the studio are asking us to preserve the grain. So you have a filter inside the codec that is good for coding and managing all the information, but the grain is something that is more random and a bit hard for an encoder to do the encoding. So there is the availability in everyone to remove the grain from the video, and to compute the grain at the decoder side by sending some parameters of the film grain synthesis. And you can achieve, here I put only 27%, but we can achieve even more than that on a lot of content. So on our side, we did some performance analysis. So the initial software was really slow. Now it's not at the same level. It's still hard to compare because you have a lot of assembly codes that you don't have in general at MPEG. So now it's 5 times slower than HEVC. On our side, we try to constrain the two codecs to have similar structure for the frames for the GOP and also the QP to have similar also value for the QP. And then we went to also similar values for both AV1 and HEVC. So saying that AV1 was a bit better, but only 10% better than HEVC. And for people looking at the video, it will be difficult to see the difference. Then I go to NP5 part 1, so HEVC, so with a standardization effort starting in January 2019. So it's the response was coming from, the best response was coming from an alliance, Samsung, Huawei, and Qualcomm. And the idea is to have an international standard for the next meeting, so in July 2020. So you have two profiles, which is quite important. The baseline profile, which is with a royalty-free declaration. So it's using 20 years old technology, so there is no patent ongoing on this particular technology. And the main profile that is adding some tools, mainly tools that are coming from VVC, but provided by this particular company, Samsung, Huawei, and Qualcomm. They are saying that they will come up with a royalty-friendly fee. So I don't know how friendly it will be, but let's say if we are friends with Samsung and Qualcomm and Huawei, we should have a good fee. Something that is quite important and that you should notice is that the decoder, if the decoder is capable of decoding main profile, it will be able to decode also the baseline. Why is that? Because main profile is a superset of the baseline profile. Some values, which I think are quite important here. So if we look at UHD, the difference between EVC and VVC will be 10%. The encoding time is twice in between the two, so that's why you are having a better compression ratio with VVC over HEVC than with EVC. But still, it's still good. So there was some codec that was not adopted earlier at MPEG, but maybe this one will be adopted faster than VVC. I cannot predict, but this is an alternative that we are having today. And if we look at the baseline with royalty-free codec, we are having something that is at 38% improvement over AVC. If you remember correctly, it's really close to what HEVC is bringing over AVC. So the encoding time here is a bit difficult to manage over AVC. AVC has a quite old structure, but it's faster than the codec of AVC at the moment. We could say more than they are at the same level rather than it is faster, but this is how it is as of today. And the decoding time is not bigger than the decoding time of AVC. And we are having similar results from the interdigital presentation. So just to conclude, so we are having, let's say, this year 3 main codecs. One that is in advance compared to the others because it's released, that's AV1, and the hardware is available. We can do 8K with AV1 on several TV vendors, so that's really something that is impressive to everybody. You can do HDR from the very first time with this particular codec, so that's also quite important, is that the adoption of HDR is coming from the very beginning here. And you have two other codecs that are VVC and EVC. So VVC is the best codec, but also the most complex. It has the versatility, so it can do a lot of things on what Ian was explaining. And you have many people, so many companies that knows how to do codecs. So that's the maturity in the ecosystem is not, you cannot make any question on that side. HEVC main, so it could be a good contender to VVC. The success may depend on the royalties of VVC. So I urge also the guys from VVC to do to manage the fees, and something that is quite important that HEVC main is including HEVC baseline. So you have also the capability to have a royalty-free codec part of HEVC. That's all for my presentation.
Thank you very much, Michael.
Yeah, you can go.
Thank you very much, and yeah, perfectly on time again. Well done. So we'll hand over to Jean-Baptiste. A quick one, maybe. We have got a couple of questions, especially comparing VVC and AV1. Is there any coding percentage gain that you have in mind between VVC and AV1? Or any
between
VVC and AV1?
VVC or EVC? Maybe I should read the question.
Yeah,
so VVC will have around at least 25% over AV1 based on our analysis at the moment. So which is quite important as of today. What I am demonstrating here is so VLC. So from the, are you seeing my screen still or not?
Yes.
So I put the full screen. So sorry for the other icons that I have on my screen. So it's the first demonstration that we are doing with Video Lab or Video Labs, because that's the company that is part of the project. So I call Video Labs. So that's the real-time VVC implementation that we are doing. So here I'm just decoding the TS just for the purpose of the demonstration. But that's a first real-time decoder implementing into Video Lab. So you cannot have access to it because the standard is not yet finished. So it's not a standard bitstream or compliant bitstream for the standard, but that's an early demonstration that we can do. We can do that in 4K as well, but my laptop is not capable of decoding it in real time. So I'm using HD here, and that's the first demonstration that we can do. More to come, I would say. In a few.
Thank you very much again.
JB, I'll let you
move to the next one. Yeah.
Hello, do you hear me?
Yes, we can.
Okay, so my name is Jean-Baptiste, and I'm going to talk a bit about a different side of the Codec Wars, which is the video LAN view. A contrario from my co-presenters, the difference is that I have a very have a big bias about implementation in actual software players. Lots of discussion about HEVC and VVC, about broadcast, and a lot of people using VLC or other open source software are using it for OTT, but also for pirated content, for video encoding, for video conferencing, and so many others. So we have a different view a bit about what is happening on the Codec Wars. So I'm the president of Video LAN. I've been working on VLC since now a long time. I've been developing and now managing the projects of Video LAN, which is including VLC, but other software like X264, which is one of the most used H264 encoder, and also David, the AV1 decoder. We are part of Video LAN. Video LAN is a very old project that was started at the École Centrale Paris in south of Paris And the goal of the project was to have a streaming solution that was open source. And the VideoLAN project got an encoder, which was X264, but also a server that was doing DVB streaming, and so many other tools that are either used by VLC or used by other projects. The important part was that everything should and was supposed to be open source. Of course, the most known one is the cone, which is VLC, which used to be called VideoLAN Client, and is probably one of the most used software in the world, probably in the top 10 on Windows, on Mac, on Linux, and everywhere. It got popular in the early 2000 years when, like, the video codec landscape was a mess, and because, like, people were downloading or sharing videos from everywhere, and like there was so many codecs to use, and every time, like, the main use was like you install a player and then you install a codec pack, and like this never worked. Like you downloaded those codec packs with lots of spyware and adwares, and then you added a new codec pack. While when VLC came on Windows and Mac, it just played everything, because we use our own codec that we ship and we tweak. Doing that was quite a good idea because, as you probably all know, it's not just about the codec, right? It's about the format, it's about the subtitles, it's about the metadata, and like many stuff don't work correctly in each other. Of course, everyone is focusing today on video codecs, but it's a lot more complex than that. Subtitled codecs, which seems very simple when you're just on the broadcasting side, is a complete nightmare when you have user content generated. So VLC got popular because it was able to play everything, and which give us like some interesting feedback and interesting use case of the players. Mostly, like, we've seen a lot of different codecs and a lot of people claiming a lot of things, and most of the time the claim of the industry and the people selling encoders or decoders are completely are very far from real life. So VLC also got popular because it was on numerous platforms, and Windows and Mac and Linux, but also on Android, on iOS, and so many others. VLC can do a lot of things because it's actually not a video player, it's an open source framework, and you have multiple modules, and one of them, each codec is one of the modules. So for example, now we have versions that work and can do VR. We have, as I said, VLC that is running, of course, on all the VR headsets, but on Windows, on Mac. We even still have people using VLC on OS2, which is like probably 3 people in the world. And we keep having VLC working everywhere and playing everything, which is important because while the OTT players are just like caring about the current version for what they're streaming, there is a lot of video use cases that are outside of those main use cases. And therefore VLC become like the reference tool to play a video at the point where even people who say, well, this video doesn't play in VLC, it means that the video is broken. And well, that is not always the case. Maybe there are bugs in VLC. So as I was saying, VLC has a very modular architecture with a very small core that is around 100,000 lines of code. And then you add modules, and each modules are doing different things, especially decoders, but also muxers, demuxers, encoders, decoders, or even interfaces that are based on that. And on top of this core, there is like a thin layer called libVLC, which is a library which allows us to build applications like VLC, but many other applications that you use on day-to-day and are using libVLC on the back. Think about it like as a player SDK. So the thing is, as VLC is modular, and because it's very easy to add features, and it's also easy to add stupid features. So I'm going to show you a few stupid features in VLC. So for example, you probably don't know, but VLC has a VNC and remote desktop client on it. You can do screen casting with VLC. You can do many walls that a professional wall that you're seeing at stadiums or on different pubs and bars are basically based on VLC. And of course, we support karaoke and weird format like MIDI. And like VLC is used at the QA, and you can even use it like in command line and also display on command line, which is one of the fun features. It's important to speak about those features. It's just like means and show how versatile is VLC, and also why what we are seeing is probably a bit different from the other people in the industry, especially when we start seeing about which codecs are actually used. We have, of course, Android and Android TV applications that are using libVLC, or Apple TV versions, or Android TV versions. So that's basically what I've been doing since quite a few times. VLC is quite popular, and like for the last 5 years, we're supposed to die because everyone is going to watch Netflix. And what we are seeing is the opposite. We see more and more usage on VLC. What is different on VLC compared to any other players and around is the open source community. Everything done on VideoLAN, X264, FFmpeg, and other multimedia tools from the open source community is done by people who are mostly working on their free time. They do that because it's fun, because it's technically challenging, which gives like a goal of being perfect, and which is a goal of doing the best quality and the best code, and not only because marketing or because there is IBC in 6 months or 3 months and you need to ship something. We do things because it's fun, and so we have like a very unique way of caring about technical quality. And of course, part of this community is called FFmpeg. So FFmpeg is basically a set of libraries and programs that are called self-called the Swift knife of multimedia, and is used now absolutely everywhere. It wasn't supposed to be like that, but today it is. It, of course, decodes, encode, transcode, but can mux, demux, remux, have device input, adaptive streaming. There is a lot of filter for scaling, resamplers, chroma conversion, works on every platform, and it's basically used everywhere from VLC, Chrome, Firefox, most Linux distribution, but also a lot of smartphones, a lot of smart TVs. When you start looking at it, there are so many people actually using FFmpeg. And this software, which is implementing all codecs and all formats, is absolutely used everywhere, also in the industry. It's often hidden, right? Because you have a nice UI from Harmonic or whatever. And basically, it's just rewrapping FFmpeg and with custom patches. Notably, FFmpeg was one of the reasons why software like VLC became popular, because very early it implemented all the codec families. Of course, all the MPEG-2, DivX, H264, HEVC, which came from the Open HEVC project, but also all the VP families, the WMV families, and lots of legacy codecs or game codecs that no one supports anymore. People did not care about those because, like, who watches still this codec is an often sentence that we see. But in fact, a lot of people actually care because they have files that they don't want to transcode, or because every transcoding is degrading the file. And as like the world is not as black and white as people would like to tell you. And so like, even if 10 to 20% of the codec we are seeing in VLC are outside of the main one, it's important enough that people will say, well, this player can play all the main codecs and also the other ones. Of course, FFmpeg also does the same for audio codecs, and it became very popular because it was one of the best way to interface with X264, which is the H264 encoder done by VideoLAN, who is probably one of the best H264 encoder, except the one from Atem, I think. And that was like the best way to interact with H264. You can put any file that FFmpeg was reading and put that in H264 format. Then we got like other encoders like 265, Xvid, and of course, lately libvpx, SVT. And now what we're seeing is a lot of non-open source codecs are basically based on FFmpeg. So people come with a new codec and they say, well, you know, if you want to use this codec, this is a patch how to use our codecs to FFmpeg. So the default now on the industry is to base a lot of multimedia pipeline on FFmpeg. I won't comment too much if that's a good idea or not, but that's the truth. And from that arises a big question is that how can so much people in the industry and the video industry depend on a software that is done by open source people who are working on their free time on FFmpeg, while most of the company are not contributing at all? So as my co-presenters spoke quite a bit about MPEG codecs, I'm going to speak more about the AOM part, which is the other ones. So for different reasons, VP9 was a semi-failure like HEVC. HEVC is a semi-failure mostly because of the licensing, which was literally insane and is still insane today. VP9 was a different kind of failure because it didn't have that much support from the industry. It's a good format. We could discuss about the numbers, but basically, especially with the improvements of the encoders lately, it's on par with HEVC more or less. The royalty, it's royalty free, so royalties are okay, but de facto it's very rarely used. What we see from VLC, not many people play VP9. VP9 is used basically by YouTube and Netflix and Facebook. And that's it. No one from the broadcasting industry uses it, and almost no one from the user-generated content and anime industry uses that. So based on that, they decided to do AV1, which was based on VP10, but not only. It came from several codecs, one which was Dala from Mozilla, Tor from Cisco, and VP10, and then they mixed that and gave AV1. They got quite good results. That they're happy. And that's mostly the part I'm interested in, is that we're going to see quite a few new formats and video codecs in the future, VVC, EVC, the VNova 1, and so many others. And AV1 is here, but AV2 is there in 2 or 3 years, and so on and so on. And you cannot have everything hardware accelerated because that starts to become too big on the chip die, and that's costing quite a bit of money. And also, like, hardware comes around 1 year to 2 years after the format is finalized. But in order to arrive at the something that is production ready, it gets more difficult because then you have so many legacy laptop and desktop, also because people start to renew less their laptop and their desktop or even their phone that they used to be. So the idea was to see if we could do an actual very good software decoder, which means something that it was very well designed and also where we spent all the time possible for any game. As we say, any cycle is valuable. So we launched that at the end of 2018 after the format was basically finished. And the last release is now 0.7 and is now shipped in Chrome, in Firefox, in de facto now Edge. It's also the AV1 codec that is shipped with Windows. It's on all the Linux distribution, and it's on quite a few Android applications from big providers. So it's very fast because when we see on the desktop, we're talking about on a normal desktop, we're talking of very quickly on 1080p around 200, 300 FPS. And of course, when you arrive at 200 and 300 FPS, the problems and what is limiting you is probably not the codec, but everything around in the player. This decoder is very fast on the desktop, but then most of you are going to say, well, we don't care about the desktop, right? The desktop is easy. However, there is something interesting is about the actual decoding complexity that we see. right? Because like every time you listen to people from MPEG or you listen to people from AOM, the information they give on the codec complexity is what they compute from the reference software, and it's very different from actual real life industry proven decoders. Especially because depending on how the AV1 or other codecs are structured, some are way easier to optimize for, especially with more threading more threading options. For example, FFVP9, which is a very fast VP9 decoder, which was the base of David for AV1, is actually quite a bit faster than FFH264, which is the FFmpeg H264 decoder, which was also quite well optimized. And that was quite a surprise, because when, if I tell you that VP9 is less complex than H264, you would say, no, that's not possible. Maybe it's not, but it's de facto, mathematically, it might be more complex, but in real time, in actual good implementation, it can be faster. And we see the same with AV1. From the beginning, I thought, like, when we started, we thought that HEVC was around twice as easy to decode than AV1, or AV1 was twice more complex than HEVC to decode. Well, maybe that's true. Maybe the HEVC decoder from FFmpeg is not the best or the fastest. However, what we see is that David is very close in complexity from the software decoder from FFmpeg on HEVC. And it's important because this HEVC decoder from FFmpeg is one of the most used software decoder. And of course, like, now you're going to tell me, yeah, but what we only care about is mobile, right? Because the fight is on mobile. Well, everyone is, with David, is quite fast on mobile. If you use some stuff like the Droidex, which is like mid-range phone from like 3 years ago, like 1080p 60 is clearly doable. You can even do, and of course, that's stretching a bit the point, but for the Snapdragon 410, which is very older and also like a lower range, you can do 1080p 40. And if you start to have like the high chips from 2 or 3 years ago, like the Snapdragon 835, we're talking about 100 FPS on a mobile phone, and we are not maxing the CPU at all. I'm not talking about the iPhone results because they are so impressive that this will give you like some bad ideas. However, if we start looking at the maximum stuff that we can do even in single thread, just using one core in single thread, we see that with the latest phones, we can do 55 FPS on the Xiaomi Mi 9, which is probably one of the fastest phones ever on Android. But even if we go back on the Pixel 3 2.5 years ago, the Pixel 2, we are seeing 30 FPS on single thread. And of course, all that is 1080p. So we went further and tried to see how much we could, like, how much performance we could get on mobile, and mostly, like, what about using only the small cores? As you probably know, on mobiles with ARM, you have like big cores and small cores. The small cores are around are less power expensive and therefore are better for your battery life. Because all the time you start to talk about software decoders, people say, yeah, but what about battery life? So we tried to only activate the little cores, what we call the little cores. And what we've seen is that starting with only 2 cores, well, 2 threads, you can see that David is already able to decode 1080p only using 2 of the little cores. And you see David on 821. 821 is this Pixel 1, which was like the flagship of Google now more than 3 or 4 years ago. And then you see for all the generation, which is 835, 845, 855, after 2 threads, you use basically 2 small cores and a bit of the main core, and you already can do 1080p 24 FPS. That is quite impressive, and that shows that if you want to have a good decoder, you can have it, and it can also be very competitive in terms of performance per watt, because when you start looking at hardware decoders, sometimes they consume quite a bit also. Well, why is David so fast? It's because he has a weird threading model, which is both tile thread and frame thread, but also it is an actual dual pass decoder, which is something that you don't usually hear about, right? Everyone knows about two-pass encoding, but two-pass decoding is weird. Everything is handwritten assembly, and everything is in C, of course, but everything then rewritten in assembly with no intrinsics. And when you compare to X264 or LibAV codec, now you see that David is around 25,000 lines of C, but 80,000 lines of assembly. And that means that there is as much assembly in David than the whole FFmpeg LibAV codec. That's the cost, right? In order to do a good codec, you need to spend an insane amount of time writing assembly, but that's how you can get a very fast decoder. And I will finish on that. What is the future of decoders is going to be around mixed CPU and GPU decoders. Because of course, you can expect to have like fixed function and hardware decoders, but they won't come soon, right? They will come later. However, today, most of the phone can do compute shaders or Vulkan shaders. And so we try to do some parts of the decoding actually on the GPU. So we modified last year David to be able to offload mostly the last part, which are the loop restoration filter, the CDEF or the film grain, directly in compute shaders. And what we've seen is that basically we don't get faster, we don't get more FPS. However, what we see is that we're around 20 to 25% better in terms of battery life when we play with an actual player. And thank you. That's all for me.
Thank you very much, Jean-Baptiste. Very interesting. Thanks a lot. We have a couple of questions in the Q&A. So the first one is, what is the licensing model behind VVC? I'm sure we want to reply to this one. This is for a question for everybody, and guys, I'm sending the question to everybody.
Yeah, Jan, you want to start or?
You mean the VVC licensing model? Yeah,
Yeah.
I can say a few words, although I would say, you know, your presentation probably covered the licensing aspects more. Yeah, I mean, it's tough, right? You know, the ISO and ITU, they don't do licensing, so it would be up to the participant who hold IPR rights to do their own licensing. Now, of course, based on the previous codec standard, let's just talk about HEVC. You know, people realize what a big mistake it is to have 3 pools. And also some individual companies not being in any of these pools, just like Mikhail mentioned just now. So therefore, I think, you know, how is it going to be? I think if you participate in VVC, you do see the companies being very conscious about that HEVC mistake, quote unquote mistake. It is still, you know, being deployed now. But people are very motivated to find, maybe form fewer pools, you know, more quickly, and have more clear licensing terms out more quickly to motivate implementer to use VVC. So I personally am more hopeful because, you know, what happened to HEVC in the first few years, it was kind of, you know, getting started much slower than it should. And people do realize that mistake. So I think people are motivated to solve that. But how it's actually solved, you know, I think it's certainly like single pool would be the most ideal situation. And, you know, let's see whether that happens very soon.
Something that I can add is that part of the media coding industry forum, there are several pools that join already. So I would say that the initial mandate of the media coding industry forum is to look at this and to look at what the fees could be. And what I was saying is that yes, there are several patent pools that was part of that are managing the HEVC patent pool that are part of this particular media coding industry forum. So that's true that they are taking care about it now.
Another question that came through the chat.
Yeah.
Yes, so now go ahead, Jan. Feel free to add.
No, I'm done. Sorry. Yeah, go ahead.
No. Another question that came through the chat, still on the VVC. Do you know if there is any player today or decoder available for VVC?
So what I was saying during the presentation is that since the specification and the bitstream is not frozen yet, what I have been showcasing is not a true VVC decoder. It's a VVC decoder at a given period with VVC bitstream that will not be compliant at the end. So up to now, the demonstration that I have shown is dedicated to a preliminary version of the reference software, and that is based also on our encoder itself. That is based on a given version of the reference software, so of the decoder. And so we work with INSA, so the French Institute in France, and Videoland to have a preliminary demonstration, but just to let you know that it cannot be used for let's say true deployment in the end, because the bitstreams are obsolete in a few. So we are waiting for July to be able to showcase true VVC bitstream and to showcase it to the community more widely. So the initial demonstration will not be standardized bitstream. It's too early right now.
Question maybe for Jean-Baptiste in the chat. Does VLC for Android TV already support everyone with David?
Yes, of course. VLC for Android TV, VLC for Android, for Apple TVs. We have already users using the libraries which are already using libVLC to have AV1 decoding quite quickly. And that's one of the reasons people use that. And there is another question I'm seeing, which is, why are the iPhone results so much more impressive? I have no idea. I don't understand how Apple CPUs can be so fast, seriously. What we are seeing is maybe sometimes twice or more faster than the top Android phones. That is very weird. It should be fast, but it shouldn't be as fast, to be honest.
Perfect. I don't have any more questions in the Q&A. If anyone has any questions, feel free to do it.
So David, I would like to thank Jan and Jean-Baptiste to join this particular webinar, and I hope that the audience also was having good time with us. The idea was to give the full landscape of what we have today. So we have a latest question that we still have time to answer it.
Yeah, maybe just the last one. Go ahead, guys. You can see the question, right? But I will say to everybody: is there SDK on VLC to customize features, and which company focus advanced layer on top of VLC?
Which was also related to a question that how do we make money for VLC? We don't make money for VLC. We make money on people integrating the VLC SDK to have players, and therefore people pay for that. We have various plugins that are different. For example, we've been working with a few people like Eurosport, where we have a low latency version of VLC, which can give around 45 to 60 milliseconds glass to glass latency from the encoder to the decoder through a network. And we have so many customization around VLC. Some of them go back to the public, some don't, depending on how custom they are. But yeah, a lot of customers are using VLC to do different stuff. And low latency is a big topic those days.
Thank you, Jean-Baptiste. I guess this will conclude then the webinar for today. Indeed, once again, thank you very much, Jan. Thank you very much, Michael. Thank you very much, Jean-Baptiste, for joining and speaking today about this subject. Thank you to all the attendees for joining. The recording will be available in the coming hours and days. Feel free to reach to your ATEM representative, the sales or the contact that you may have, and we will be able to send it to you individually, as well as the presentation that in a PDF format. We'll try to double check that with Jan and Jean-Baptiste after it. Thank you very much, guys. Much appreciated. I wish you a good day ahead, a good night for you, Jan. Good luck for tomorrow morning, and talk to you very soon.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye.